Hey guys, so here's another classic rotation question that we're going to use conservation of energy to solve, and it's a yo-yo question, right? So we have a simple 100-gram yo-yo that we're going to release from rest. Now, simple just means that you're going to be able to make some assumptions to simplify the yo-yo. Yo-yos are actually more complicated than how we're going to solve them, but here we're going to simplify it. That's what simple means. It just means, go nuts with simplifications. All right, so mass equals 0.1 kilograms. It starts from rest, V initial equals 0. It falls and rolls. Yo-yos do that, right? So they're falling and rolling on the way down. Unwinding the light string around its cylindrical shaft. So as it falls, it unwinds a light string. Yo-yo has a string around it. Light string means the mass of the string is negligible around its cylindrical shaft, and that's because a yo-yo has a thing in the middle. The cable, the string is here, but then the yo-yo usually has sort of an outer casing like that, right? The idea is that what matters is this inner radius, not the outer radius. The outer radius just covers the outside. So effectively, we're gonna just worry about this and say that a yo-yo looks like this. Okay, let's actually put the little string here. Now, if the string is here and you release a yo-yo, it's going to fall and it's going to roll like this. So if the string is on this side, it's going to go like this. This is the velocity of the center of mass. And it's also going to spin with the omega. Okay, so the radius of the inner, which is what matters, is 2 centimeters, so 0.02 meters. It says if the yo-yo can be modeled after a solid disk, in other words, treat this thing here as a solid disk, right? Which is what we're going to do. In other words, I will be half mr squared because that's the I for a solid disk. I want to know what is its linear speed after it drops 50 centimeters. So it drops 50 centimeters. So I can think of this as the height initial, right? This is 0.5 meters. I can think of this as the height initial was 0.5 meters. And the height final, since it falls, being 0, okay? Even if the floor is farther below, you can just move the floor up and say, I'm gonna call this point 0, therefore this point is 0.5, okay? That's how you're supposed to do it, all right? I wanna know the final speed. It's released from rest, so the initial velocity is 0. I wanna know what is the final speed. That's part A. For part B, I want to know what's the final angular speed. So what is the linear speed and what is the final angular speed? So what is omega final is what part B is asking. We're going to use conservation of energy to solve this because I have a change in heights, change in velocity. But before I do that, I want to remind you that whenever a rope pulls on a cylinder, on a disc, or on a pulley, something like that, V rope equals R omega disk, where R is the distance between the center and where the rope pulls. In this case, the rope is pulling all the way at the edge of this inner cylindrical shaft. Remember, there's another one here, but we're ignoring that. The rope, the string is pulling at the edge of this inner cylindrical shaft. So we're just going to do this. The radius, the distance is the radius because it's at the edge. So you can say that V equals R omega. Okay? So that's going to be an equation that we're going to be able to use, and we're going to have to use. All right, so let's go up here and we're going to write kinetic initial plus potential initial plus work non-conservative equals kinetic final plus potential final. Okay? Is there a kinetic initial? No, there's no kinetic initial, and that's because it's at rest initially. There is a potential energy because you have some heights. There's no work non-conservative. You're not doing anything. Even though you're holding the string, you're not actually giving energy to the system, right? So you don't do any work. There's no friction. There is kinetic at the end, and there is no potential at the end because we're moving the ground up, so to speak. And that's the lowest point, and at the lowest point of a motion, your potential energy is 0. So basically, you have all your gravitational energy goes into potential, all your gravitational potential goes into kinetic. So let's expand this. mgh initial equals. Now here, kinetic final, you have to figure out, is it linear or is it rotational? And in this particular problem, it's both linear and rotational. That same object has linear and rotational energy. So what we're going to do is we're going to do half mv squared, final, plus half I omega squared, final. Now the next step is to expand I and omega, right? Or rewrite omega, I should say. So this is going to be mghi equals half mv final squared plus half, and you're going to see how this cancels really nicely. The answer is going to come out really simple. And I is going to be half mr squared. And if you hold off on the temptation to just plug in numbers, this is actually going to become pretty neat, pretty simple once you see it. So remember when you have V and W, what you want to do is rewrite W in terms of V, so that instead of having a V and a W, you have a V and a V. That's fewer variables, that's better. So from here, I can write that W omega must be V over R. So I'm going to plug V over R over here. And when you do this, notice that the R's will cancel, right? The R's almost always cancel. It pretty much always cancels, but you got to be careful about that. Don't get trigger happy and start canceling stuff. Notice also that the masses cancel, right? Because I have a single object, so all of these M's are referring to the cylinder, to the cylindrical shaft here, to the yo-yo itself. And that mass shows up in all three terms, so I can cancel the masses. So the M's canceled and the R's canceled. All right, so let's clean this up a little bit. I'm going to multiply both sides by 4 because I want to get rid of this quarter right here. Okay, so I'm going to get 4gh initial. This half becomes a 2v final. And then this quarter becomes 1. So this whole thing is gone. And the only thing that's left out of this whole thing here is the v. So it's v final squared. This is obviously 3v final squared. And if we're solving for v, just got to move the 3 over and take the square root. Okay, so v final is the square root of 4 over 3 gh initial. And this is pretty cool, borderline cool, in that notice that it doesn't depend, I'm going to write this here because it's really important actually, it doesn't depend on m or r. So the final velocity of a yo-yo has nothing to do with its radius, has nothing to do with its mass. It only depends on obviously the gravity. It depends on the initial height. The higher you are, the faster, the more you drop, the faster it will be. And this 4 over 3 here comes from your moment of inertia, from your shape. So if you have a different shape, this will have a different fraction here. Okay? So it could have been, I don't know, I'm going to make something up. It could have been 5 over 2 if you have a different shape. Okay? But so that's one point. A second point that I want to make is that in these rotation problems, the form of the answer is very similar to their linear counterparts. What the hell did I just say? Imagine if you drop a block, and after the block falls a height of h, we can calculate using motion or energy, but you may remember this, that the velocity at the bottom is the square root of 2gh. You might remember this, right? This is for linear motion. Okay, this is like a separate thing. Now look at how similar these two guys look. This is very similar to this. The only difference is that this has a 2 and this has a 4 over 3. So that's what I mean by the form, the shape. The equations look similar to what you would have expected in linear motion. The difference is that the coefficient is different. Another thing is that the coefficient is less. So in rotation, same form, the equation, the answer will look similar to linear. It has a different coefficient, and the coefficient is not just different, but it's a lower coefficient. Coefficient is just a number in front of something else. Okay? 4 over 3 is 1.33333, which is lower than 2. What this means is that if you drop a block and a yo-yo, the block will fall faster than the yo-yo. And that's because the yo-yo has two types of energies. The block only has linear. The yo-yo is converting its potential energy into both linear kinetic energy, which makes it fall fast, and rotational kinetic energy, which makes it spin. So because it's spending energy into spinning, it actually falls slower. In theory, if this yo-yo were to spin at this at infinity speed, it would actually never fall because it would be busy spending all of its energy in rotation. So hopefully that makes sense. The reason why I want to point this out is because you can use this as a way to verify if you're correct. For example, this fraction could never be greater than 2. And if you ever do a question like this, where you end up with a number that's greater than the coefficient in the linear version, if you happen to remember the linear version, then you know that something's wrong. If I gave you, for example, a question where instead of the yo-yo being a solid cylinder, but instead we had a hollow cylinder, the solution would be exactly the same. The only difference is that this I over here, this number in front of the I would be different, and that difference would sort of work its way through the problem. That's this half right here. This half is this right here, right? And you end up multiplying, blah, 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 so you end up with a fraction that's different. The 4 over 3 would be different. But whatever that number is, it would be less than 2, okay? So just trying to give you sort of an intuition in terms of how linear and rotational problems that look very similar also have very similar answers, just slightly different. Cool? That's it for this one. Let me know if you have any questions. Let's keep going.